friends, I am Tehseen Khan, Assistant Professor at B.Pharmacy College, Sagar. Today we will deal with a learning episode of B.Pharm on the important topic entitled Potentiometry, which is scripted by Dr. Ankur Vaidya, Assistant Professor, Pharmacy College, Safi, UP RIMS and R. Etawah. So let's start our episode while taking a look at what we are going to learn today. Introduction. Potentiometry is the field of electroanalytical chemistry in which potential is measured under the conditions of no current flow. It is a classical analytical technique with roots before the 20th century. However, the rapid development of new selective electrodes and more sensitive and stable electronic components since 1970 has tremendously expanded the range of analytical applications of potentiometric measurements. Selective potentiometric electrodes are currently widely used in many fields including clinical diagnostics, industrial process control, environmental monitoring and physiology. The measured potential may then be used to determine the analytical quantity of interest, generally the concentration of some component of the analytic solution. The potential that develops in the electrochemical cell is a result of the free energy change that would occur if the chemical phenomena were to proceed until the equilibrium condition has been satisfied. These methods rely on the quantification. A number of common references and ion selective electrodes are reviewed along with general calculations and analytical approaches. When a potentiometric titration is being performed, interest is focused upon changes in the EMF of an electrolytic cell as a titrant of known concentration is added to a solution of unknown. The method can be applied to all titrimetric reactions provided that the concentration of at least one of the substances involved can be followed by means of a suitable indicator electrode. The critical problem in a titration is to recognize the point at which the quantities of the reacting species are present in equivalent amounts. The titration curve can be followed point by point, plotting as ordinate successive values of the cell EMF, that is pH, versus the corresponding volumes of titrant added. You can see the figure number 1 represents potentiometric titration curve in between EMF on the y-axis versus the corresponding volume of titrant added. Measurement of potential. Potentiometer is used to determine the difference between the potential of two electrodes. The one electrode is working or indicator electrode, the one electrode which responds to the analyte's activity, and the other electrode is the counter or reference electrode, has a known fixed potential. Reference electrode, generally used as hydrogen electrode, calomel electrodes and silver chloride electrodes. The indicator electrode forms an electrochemical half cell with the interested ions in the test solution. The reference electrode forms the other half cell. The overall electric potential is calculated as E cell is equals to E IND minus E reference plus E sol. E IND is the potential of indicator electrode. E sol is the potential drop over the test solution between the two electrodes. E cell is recorded at intervals as the titrant is added. Reference electrode is a half cell with the accurately known electrode potential. E reference is independent of the concentration of the analyte or any other ions in the solution, which always treated as the left-hand electrode. Indicator electrode is immersed in a solution of the analyte, develops a potential E end, depends on the activity of the analyte and is selective in its response. Location of endpoint is potentiometric titration. The endpoint is determined by a number of methods. Some of them are summarized here. A. Titration curve. Titration curve is obtained by plotting the successive values of cell EMF on ordinate and corresponding values of volume of titrant added on the abscissa. This gives an S-shaped curve. The central portion of this curve shows the steeply rising portion corresponds to the volume for the end point of the titration. When there is a small potential changes at the end point, like in the titration of weak acid with a strong base, titration of very dilute solution, etc., it is difficult to locate end point by this method. Friends, here you can see the figure number 1, which represents titration method of locating end point. B. Analytical or derivative method. In this method, the end point can be more precisely located from the first or second derivative curves. The first derivative curve involves the plot of slope of the titration curve, delta E by delta V, that is ration of change in EMF and change in volume added, against the volume of the titrant added. Most frequently, delta E by delta V is plotted against the average volume of titrant, added corresponding to the values of EMF taken. Volume on the x-axis corresponding to the peak of the curve is the endpoint of the titration. Coming to our next figure 2, first derivative curve. In second derivative curve, we plot the slope of first derivative curve, that is delta square E by delta V against volume. The point on volume axis where the curve cuts through 0 on the ordinate gives the endpoint. The point corresponds to the largest, steepest point on titration curve and maximum slope of the delta E by delta V curve. Above mentioned methods need values of potential corresponding to very small change in volume of titrant added near the end point of good result. In the immediate vicinity of the end point, the concentration of the original reactant become very small, and it usually become impossible for the ion to control the indicator electrode potential. The cell EMF become unstable and indefinite because the indicator electrode is not longer bathed with sufficient quantities of each electroactive species. Therefore, the above methods may not give satisfactory results. Again also, results obtained by above methods may be in error if the reaction is not symmetrical. Example, in titration of silver ion with chromate ion. Figure 3, which represents the second derivative curve. Grand plot. This is a new method of endpoint location in potentiometric titration, developed by G. Gran in 1952 and modified by others. This method does the numerical manipulation of titration curves into linear straight lines intersecting at the equivalence point. During the potentiometric titration of Ki with AgNO3, following reaction occurs. Ki aqueous plus AgNO3 aqueous is equals to AgI in solution form plus KNO3 aqueous. The cell for the titration is SCE by Ki, AgI by Ag, and the EMF of the cell is given by E cell is equals to E naught cell minus 2.303 RT by F log I. The EMF of the cell increases during potentiometric titration of Ki with AgNO3. By manipulating above equation, one can derive the following equation for locating the endpoint by Grant's method, where V0 is equals to initial volume of Ki taken, V is equals to volume of AgNO3 solution added, Ve is equals to volume of AgNO3 solution at endpoint. C, Ag plus is equals to concentration of AgNO3 solution added. F is equals to Faraday's constant. R is equals to gas constant. T is equals to temperature. Delta is equals to activity coefficient. In above equation, the term is called Grant's function. When Grant's function is plotted against volume of AgNO3 added, V, a straight line will be obtained. Such a plot is called Grant plot. Above equation best fits for the data point taken only before the equivalence point. The endpoint can also be obtained from the data point after the endpoint by plotting against the volume of titrant added. Thus, The endpoint from grand plot can be obtained either taking the point before the endpoint or taking the points after the endpoint. It is obvious that the results obtained from linear curves would be more accurate than from the non-linear ones. The linear straight line can be extrapolated to the volume axis to locate the endpoint by the development of calculator, later on computer, and using ion selective electrode. Use of grand plot is increasing. The advantages of using Grant's method of locating endpoint are simplicity of measurement, simplicity of calculation, versatility, and precision. Equipments. The basic apparatus required for all potentiometric titrations are the same and is shown in figure 4. The common parts of potentiometric includes: first, indicator electrode, used to respond to changes in the species of interest. Second, reference electrode, produces an unchanging voltage regardless of solutions changes. Most commonly used references electrode is calomel electrode. Third, voltmeter or pH meter, used to measure the voltage or pH of the solution. Next is stirrer and follower, is used to avoid the need to manually swirl the solution between additions. Next is burette, to add the titrant, of course. Dear friends, here you can see the figure number 4, which represents schematic diagram of potentiometric equipment. Analytical application of potentiometric titration. Potentiometer is a versatile tool for drug analysis. It is an alternative to UV visible spectrophotometry because of its ease of operation and easy to handle and no special dilution required. Potentiometry can couple with an NMR spectrometer results in a powerful hyphenated technique called NMR controlled titration. Currently, potentiometric titration is used for its number of applications. Some of them are summarized here. First, it is used to determine the solubility products of sparingly soluble salts. Second, it is used to calculate the pH of solution. Third, potentiometric titration is also used for assay of raw materials. Fourth, potentiometric titration is used to determine thermodynamic functions. Fifth, it can also estimate the activities of electrolytes. Sixth, determination of the endpoints in titration. Seventh is determination of pKa and pKb. Before moving to our next module, that is about direct measurements of metal concentration, I would like to suggest you to visit our website www.cec.nic.in for further readings and learning of more topics associated with your B.Pharm syllabus. Here you will find many lectures, e-content, FAQs, LORs and many more. Hope this site will be a catalyst of learning for you. Module 4. Direct measurements of metal concentration. In many situations, accurate determination of a metal ion concentration by measurement of a cell potential is impossible due to the presence of other ions and a lack of information about activity coefficient. In such cases, it is often possible to determine the metal ion concentration directly by potentiometric titration with some other ion. For example, the initial concentration of an ion such as Fe2+ can be found by titrating with a strong oxidizing agent such as Ce4+. The titration is carried out in one side of a cell whose other half is a reference electrode. Platinum S by Fe2+ and Fe3+ by reference electrode. Initially, the left cell contained only Fe2+. As the titrant Ce4+ is added, the ferrous ion is oxidized to Fe3+ in a reaction that is virtually completes. Fe2+ plus Ce4+ gives Fe3+ plus Ce3+. The cell potential is followed as the Fe2 plus is added in small increments. Once the first drop of Ce3 plus has been added, the potential of the left cell is controlled by the ratio of oxidized and reduced iron according to the Nernst equation. E is equals to 0.68 minus 0.059 log Fe2 plus by Fe3 plus. When the equivalence point is reached, the Fe2 plus will have been totally consumed. The large equilibrium constant ensures that this will be so. And the potential will then be controlled by the concentration ratio of Ce3 plus is equals to Ce4 plus. The idea is that both species of a redox couple must be present in reasonable concentration for a concentration to control the potential of an electrode of this kind. If one works out the actual cell potentials for various concentration of all these species, the resulting titration curve looks much like the familiar acid-base titration curve. The endpoint is found not by measuring a particular cell voltage, but by finding what volume of titrant gives the steepest part of the curve. In potentiometric titration, we are interested in relating a single voltage measurement to the solution concentration. We are only interested in identifying the endpoint volume of the titration by the change in voltage from one volume addition to the next. Friends, here you can see the figure number 5, which represents typical potentiometric titration curve. The common features of the titration curve includes the wave-like shape occurs because of the rapid change in voltage around the endpoint of the reaction. The endpoint break is a large change in voltage around the endpoint. The endpoint break should be as large as possible to improve accuracy of detection. This is done by choosing the titrant carefully, discussed in later section of this chapter. The endpoint volume is defined as a volume halfway up the endpoint break. The voltage values before the endpoint are due to analyte. The voltage values after the endpoint are due to the titrant. The other differential curve, including first derivative curve, second derivative curve and grand plot, have been discussed previously in this lecture. Determination of KSP. Solubility product constant is simplified equilibrium constant, that is KSP, defined for equilibrium between a solid and its respective ions in a solution. Its value indicates the degree of which a compound dissociates in water. The higher the solubility product constant, the more soluble the compound. The solubility product, that is constant or KSP, of silver chloride is given by the expression KSP is equals to Ag plus Cl minus. Potentiometric titration curve data is utilized for the determination of solubility product. The concentration of ions in equilibrium with a sparingly soluble salt are sufficiently low that the Nernst equation can be used with little error. Rather than measuring the concentration of the relevant ion directly, the more common procedure is to set up a cell in which one of the electrode involves the insoluble salt and whose net cell reaction is just the dissolution of the salt. For example, to determine the KSP for silver chloride, we could use the electrode in the cell. Other useful solid-state electrodes are based on silver compounds, particularly silver sulfide. Silver sulfide is an ionic conductor in which silver ions are the mobile ions. Mixed pellets containing Ag2S, AgX, where X is equals to Cl, Br, I, SCN, have been successfully used for the determination of one of these particular anions. The behavior of these electrodes is basically determined by the solubility products involved.